Hello, welcome to the last video for Unit 3, Reactions and Equations. This video I'm going to deal with acids and bases, just a little bit of general knowledge on acids and bases, and that will lead us into neutralization reactions. And then of course there is a unit on acids and bases later in the course that will be much more detailed than this video. So when we think about acids and bases in everyday life, just have a look at this picture in the top right here. A lot of these home cleaning products, you see things here like Drano and soda water and ammonia. There's certainly acids and bases in there. The acids probably come to mind if you were to think about food, think about grapefruit, think about lemon, lime, orange, citric acid. They tend to taste sour. If metal was exposed to acid, certainly it would dissolve many metals. And in the lab, you may have done this in junior high, where what's called litmus paper, red stays red and blue paper turns red. One way to remember this paper test is I just think B for blue and base, B for B. So blue paper remains blue or red paper turns blue. So blue, base. This is just a little way to remember this. Not that we're going to get into a lab and do this, but bases, if you were to think about something that tastes bitter and feels slippery, think about a bar of soap. There's a really easy one. So what do we know about acids and bases? Well, for the purposes of this course and in this particular unit and chapter, we need to look at what the scientist Arrhenius was able to figure out in his research. His definition basically is one that was one of the earliest definitions. We've since built upon it in more detail. But what he said is that if a compound, when it dissolves in water, in an aqueous solution, it will produce hydrogen ions, H+ ions. So for example, HCl though is covalent, so it doesn't contain ions. So we've got to think about this. That's covalent, it's bonded, the H and the Cl, they share an electron. So in water, HCl ionizes to form H+ ions and chloride ions. So how does that work? Well, it's because it happens in water. So the H+ ions are very reactive. And so a water molecule, H2O, oxygen has a lot of, as a nonmetal on the far right-hand side of the table, it has 6 electrons. So it needs 2 more to become stable. So it's called very electronegative. So the sharing that goes on between H and O here is uneven or unequal sharing. Oxygen has a stronger pull. So oxygen gets a little bit called slightly negative charge on this end, and these two hydrogens are slightly positive because the shared pairs are pulled closely to oxygen. And if those electrons being shared are coming closer to oxygen, it obtains a little bit of a negative charge because electrons are negative. So it's called a slightly negative end here and 2 slightly positive ends. So then when these hydrogen ions that happen when HCl is added to water, these H+ ions are going to be attracted to this negative bit right here. And you see that happening where H+ comes along and bonds in here. So we've got this extra plus here because this brings with it a proton, right? It's in column 1, its atomic number is 1. So this is called the hydronium ion. So this H3O+. This is what is giving us, this is what's happening here in this definition here. It's not from the H, it's the H3O+. So it's not the H and the HCl by itself, by this definition. It's what it forms in water is making this acidic. So it's the hydronium ion. The H+ ions are dissociating with the H2O molecules, and so if this H3O+ is formed, we say it's an Arrhenius acid, and that is the definition that Arrhenius gave us. His definition of bases was that a base will produce hydroxide, these OH- ions. So here's NaOH added to water, and so we've got these Na+ and OH-. So this is called sodium ion, this is called hydroxide ion. It would be in a table in your book, not to be memorized, not necessary. So an Arrhenius base, he says, basically is a compound that when added to water makes an aqueous solution and OH- ions are present. Okay, now there are some things like molecular ones, right? Molecular compounds, the ones that are definitely more into sharing the covalent compounds. This is an alcohol called methanol, and they do not dissociate in solution, so we would not call them bases even though they have this OH. It's all about the fact that NaOH has a very positive end and a very negative end, ionic bonding in here between Na and OH, so then that's why it will break apart in water. So again, just looking at this definition that we're asked to look at, acids and bases naturally combine to form water. So think about that H plus from the first example with HCl, the OH minus from the NaOH example. Within those, so this is the acidic part, this is the basic part, so acidic and basic parts form water. So let's look at the purpose of this unit, which is more specifically to get into what's called the neutralization reaction, since we're looking at types of reactions. So again, from the former few slides here, we have acids and bases mixed together, the H plus and the OH minus. So the H plus from the acid, the OH minus from the base, those two acidic and basic parts form water, and the remaining part will be an ionic salt. So K from KOH and Cl from HCl will form a salt. So this is the general formula. Acid plus base form water and salt. Here's an example over here of sodium bicarbonate. So think of this as baking soda, because it is, and baking soda and HCl. You've probably seen this maybe in junior high or high school as well. And this is your fizzy reaction where you see basically the salt is formed. Now this H2O and CO2 would have been carbonic acid at one point. It would have been the H2CO3, but it's such a weak acid it falls apart. So what's different here is that instead of water and a salt, we've got water, gas, and a salt. And it's just because of the carbonate in this very weak base. So these carbonates form CO2. We pull that out of there. Again, not to be memorized. But that fizziness here, the fizzing, that's the CO2. So there'd be pure water in there, and then there'd be the dissolved salt, which you wouldn't see either. So that's just a little reference to something you may have already seen. This is how antacids work in your belly. The HCl is actually we have hydrochloric acid in our belly, in our stomach, helps with digestion and regulation of bacteria populations. But you might say, well, boy, why would I take an antacid tablet if it's going to create gas? Well, there's actually another compound in there to help reduce the gas production. So just a little side note on everyday life example. Getting back here again, so we were looking at net ionic equations in a former video, and so that is what's important here. Now we can look at more reactions and look at what's really happening. Where's the real reaction here? It's the non-aqueous result. So it's either the liquid, the solid, or the gas. In this case, it's water, pure water. Water is a pure liquid, so the net ionic is for an acid-base reaction is how the water is formed. So here's an example question, and I actually just wrote it out for you to save on time, but I want you to use your table 4.1. What goes in here for sodium sulfate, for example? Is it a precipitate? Is it liquid? Is it aqueous? So that's left for you to do. This one is basically about showing how you understand that an acid and a base break up to make a salt and water. And then the two here, it just has to do with the balancing. Okay, so there's an example. And I'm going to leave you with these ones to try. And if you have any questions, please post them on the Q&A for the unit. Thanks for watching.